Hello and welcome to section 15.4 on Green's theorem. This is the second of the four big theorems in vector calculus we're studying this quarter. So we'll go ahead and just state the theorem and then we'll illustrate its result with the first question on the worksheet. All right, so let C be a simple, closed, piecewise smooth curve oriented counterclockwise that encloses a connected and simply connected region D in the plane. Okay, so let's take a pause there. This opening sentence is jam-packed with that new terminology we introduced in the last section. Okay, so as a reminder, a curve is simple provided it does not cross itself, okay, which we see here. It's closed provided the curve closes in on itself, or put another way, you can parameterize the path in such a way that the initial and terminal points coincide. Okay, piecewise smooth, well, the curve I've drawn here is smooth because it doesn't have any sharp corners, but more generally, okay, I could have a path like this that does have sharp corners, so it's not smooth, but each piece that makes up the path is itself smooth, and so we would call that piecewise smooth. Okay, oriented counterclockwise. Okay, so put another way, if I walk along this path C, then the region that it encloses, D, is always off to my left. All right, now what about this region D? Well, we're requiring it to be both connected and simply connected. So it'll be connected provided any 2 points in the region can be connected with a continuous path between those 2 points, which is the case here for this region. And it's going to be simply connected if it doesn't possess any holes. Remember, regions in the plane will be simply connected if they don't possess holes. And that is also the case here. All right, so now what does Green's theorem say? It says that if you compute the line integral of a vector field f over this boundary curve C for the region D, then that is equal to the double integral over this region D of this quantity partial q partial x minus partial p partial y, where p and q are just the components of the vector field f. Okay, so again, this integral on the left is over the boundary of this region D, whereas the integral on the right is a double integral over the boundary D itself. All right, so now let's illustrate this with problem 1. It says consider the vector field f, which is minus yi plus xj, and the region D, which is just the disk of radius 5 centered at the origin. It says compute each corresponding integral in the statement of Green's theorem above to illustrate their equality. Then it asks, is the vector field conservative? All right, so to compute the line integral, okay, this is the type of computation we were doing in section 15.2. We're going to first parameterize this boundary curve, which is just the circle of radius 5 centered at the origin. So I'll go ahead and do that with the parameterization 5 cosine t and 5 sine t, letting t vary from 0 to 2 pi. So that gives us a counterclockwise orientation for that circle. Okay, and so now to compute this line integral, we have to integrate our vector field f evaluated along our path, and then we have to dot that with the derivative vector r prime, which in this case is just minus 5 sine t comma 5 cosine t. And we're going to be integrating this dot product quantity from 0 to 2 pi. All right, so now to evaluate our field f along the path, well, our field f is minus yi plus xj. So we're going to replace y with 5 sine t. So that's going to give us minus 5 sine t for the I component. And then we're going to replace x with 5 cosine t. And so that's going to give us 5 cosine t for the j component. So now if I dot these two vectors, I just get a constant. I get 25. And integrating that constant from 0 to 2 pi will give me 50 pi. All right, so that's the value of the line integral around this boundary curve. So now let's go ahead and compute the double integral on the right-hand side. So differentiating Q, which is just the J component of the vector field F, with respect to X, well, I'm just differentiating X with respect to X, so that's going to give us 1. And then differentiating P, which is the I component of the field F, with respect to Y, that's going to give us -1. And then taking this difference, we're just going to get the constant 2. So this double integral here in Green's theorem is just really the integral of the constant 2 over this disk of radius 5 centered at the origin. And then that's equal to just twice the area of the disk. And the area is 25 pi, so this is equal to, well, 50 pi again. So these two integrals are in fact the same. Okay, so then for the last part of the question, it says, is the vector field conservative? Explain. Well, from the last section, we said that the vector field F will be conservative provided the line integral of the field over all simple closed curves is equal to 0. And since we got that this line integral is 50 pi, so in particular it's not equal to 0, we can conclude that this vector field is not conservative. Okay, so notice that this vector field is just the rotation field that we introduced back in section 15.1. Okay, and this line integral is just computing the circulation of that field along this boundary circle. So it makes perfectly good sense that we would not get 0 for the circulation integral, right? Because our vector field here is tangent to the boundary circle at every point. So adding up all those tangential components will not produce 0. It's going to produce a positive value, which is 50 pi in this case. But in any event, field is not conservative, and that will do it for this question. And we will just continue with more examples in the next couple videos. All right, so I'll see you there. Thanks.